Okay, so to cap off the section 11.1 sequences, we're going to talk about the monotonic sequence theorem. It's our objective in this video to introduce, justify, prove, and apply the monotonic sequence theorem. That's a lot of things at once, so I just want to warn you that you'll want to take this video in chunks. Ordinarily, I would break it up into more than one video, but I think it all goes together. So that's my reasoning for keeping it all together here. So I want to start with thinking of a sequence that is more or less okay to work with. It's not exotic, or there's nothing very interesting about it other than it is a really good example of the of how this theorem works and why it works. So consider the sequence a sub n given by a sub n equals 1 minus 1 over n. Okay, so nothing too complicated about that. The first value is, so just to illustrate, right? So we're talking about the sequence 0, 1/2, 3/4. What would the next one be? So we're subtracting 1/5, so 4/5, then 5/6, then 6/7, right? And so on. Oh, I missed one, didn't I? 2/3. Oopsie. So each time we're just removing a smaller fraction from 1, right? So it makes sense that we're getting something that is it looks like getting closer and closer to 1 without becoming 1, right? At no point in this sequence do we actually at any point have the term 1. But I want to point out two very interesting and important facts about this sequence. So first of all, the punchline is, of course, that it does converge, and it converges to 1, right? That we can see because we can apply the limit laws. We can see that the fractions are becoming, right? If we wanted to write this in another format, right, we could also write it as n minus 1 over n, right? And it's clear that that is also getting closer and closer to 1. But really, the payoff here is that, so here's 1, 2, 3, 4, 5. Like really the objective to think about here is what properties does this sequence have, and how is it getting closer to 1? So first of all, two observations that I'd like to point out to you, okay? So first, a sub n is monotonic increasing, right? This is true, right? No matter what values you pick, it's only getting larger and larger, right? So for all n greater than or equal to 1, a sub n plus 1 is greater than a sub n. Why is that? Because the difference between each one, right, is the next fraction forward. So a sub n plus 1 minus a sub n, right, what's the difference between any two terms? Is going to be 1 minus 1 over n plus 1 minus 1 minus 1 over n. The ones cancel, and we're just left with 1 over n minus 1 over n plus 1, which is a positive value, right? Because n plus 1 is larger, so the fraction is going to be smaller. The other thing to observe here is that a sub n is bounded. specifically bounded above, right? For all n greater than or equal to 1, a sub n is less than 1, right? And we see this because, again, let's think about what the alternative closed form of the nth term is, right? We had a fraction that is strictly less than 1. So, in short, there is no place for the sequence to go except for the limit y equals 1. Why? Because it's increasing, so it's never going down, and it's never going past 1, okay? So that put together is going to give us what our theorem statement is, okay? So the theorem. And in this case, I've given you an example where we literally know what the sequence converges to. We know what the limit is. But I want you to note that we don't actually need to know what the limit is because the statement itself says every bounded monotonic sequence is convergent. And there's actually two cases to break up in this theorem, right? So case 1 is increasing and bounded above. BDD stands for bounded. So that's like the example that we saw here. And then there's case 2, which is decreasing and bounded below. So as an example of this case, you can think of the sequence a sub n equals 1 over n. We know that that's decreasing, right? And it's bounded below by 0. This theorem, we can justify it briefly by thinking about, so thinking about this example that we just looked at, right? So there's nowhere for the sequence to go but to the limit. And similarly, we can think about this additional example where if you think about the graph of such a sequence, right? So this graph looks something like 1, 1/2, 1/3, 1/4. Right, this is a sub 1, a sub 2, a sub 3, a sub 4. This is a decreasing sequence, right? So it's a monotonic sequence and bounded below by 0. And bounded below isn't a unique, or bounded actually isn't a unique statement about the sequence in that you can find any upper or lower bound that you want, right? So you could say it's bounded below by -1, bounded below by -1/2, but it's definitely bounded below by 0. We know that that is for sure one of the lower bounds of the sequence. There are some words here that I'm using kind of loosely that I haven't formally defined. And so when we say lower bound, we mean a value for which the terms never get below. When we say upper bound, we mean a value at which the terms of the sequence never go above. But if we wanted to say definitively that this theorem is true, then we should prove it. And I'm going to leave that for the end of this video, okay? All I want you to know for now, though, is that the underlying reason this works, so this theorem is true because of an axiom called the axiom of completeness, or sorry, the completeness axiom as they call it in the book. That defines the real numbers. So it's one of the defining principles of the real number line. And that axiom, loosely speaking, says there is no gap in the set of real numbers. And I'm gonna formalize some of this in the proof part of this video. And I want to stress that if you are not a math major, some of this is not necessarily, it's not strictly speaking necessary for you to know this, right? But even if you are contemplating becoming a math major, I do recommend that you stick around for the end of that video, because it highlights some very fundamental underlying ideas that are not only underlie calculus, but the math behind calculus. So before we get to that, let's see an example of this in action. So this example is actually, it's going to feel very, how would we apply this? And it's actually very useful for when we have to work with recursively defined sequences. So we're going to show that the sequence defined by a sub 1 equals 1 and a sub n plus 1 equals 3 minus 1 over a sub n converges by the monotonic sequence theorem, which I may slip up and call the monotone convergence theorem, but it's the same thing. Okay, so I wanna sketch the idea here that we're gonna have to do two things, right? So step one, show that a sub n is monotonic. Which flavor is that? We'll notice that each successive one is taken by subtracting a fraction from the previous one. So whatever your intuition is saying here, let's play around with finding the first few values first, and then we'll see how to determine which one. Step two is to show that the sequence is bounded. Okay. Which one, bounded above or bounded below, will depend on which monotonic we are talking about. Okay. And step three is basically pulling it all together. We're going to say by the monotonic sequence theorem, because we've shown step one and step two to be true, it follows. Which is to say, you're literally applying the theorem as it's stated, right? Because the sequence is monotonic and bounded, then it must converge. And then at the very end, we'll also see how what it actually converges to. It's actually very fun. Okay, so one last thing that I have to address before we actually get into this is we're going to do step one and step two by something called mathematical induction. And what mathematical induction is it's basically a way for us to prove statements that are general to all the natural numbers. Okay, so when you want to show that something is true for every natural number, for every n, right? So that this pattern holds for the entire sequence, in other words, then you have to use mathematical induction, okay? And as an aside, what are the steps to that? Well, I'm gonna highlight them, but there's basically three steps to it, okay? So there's what we call the base case, which basically relies on show that it's true for the first or the second natural number, or maybe both. The inductive assumption, which is we're going to assume it's true for n equals k. And lastly, we're going to apply the inductive assumption on the k plus 1th step, which is basically showing that this this pattern will hold for the k plus 1th step, okay? So I'll walk you through all of that. It's not terribly difficult, but you have to be aware of what you're, sorry, I'm distracted by my crying daughter right now because she's refusing to take a nap, but not to worry. So what is our claim here, right? So remember, we had 3 steps, and 2 of them are going to rely on mathematical induction. So the first one is step 1, show that A sub n is monotonic. So our claim, so remember, this is step 1. The claim is that for all n greater than or equal to 1, A sub n plus 1 is either going to be greater than or less than A sub n. In this case, it is going to be greater than, okay? Why? How do we know this? Because we're going to show the base case, okay? So let's go to the base case, which in this case, we're going to say n equals 1, okay? So, A sub 2, remember, we're going to use the recursive part of the recursive definition of the sequence, is 3 minus 1 over A sub 1, which is 3 minus 1 over 1, which is 3 minus 1, and A sub 2 equals 2 then, which is greater than 1, which was A sub 1. Okay, so all this is to say, A sub 2 is literally equal to 2, and A sub 1 is equal to 1. The base case shows that it should be increasing. Okay. All right, now the inductive assumption. So we're going to suppose for the n equals k case that A sub k is greater than A sub k minus 1. So the very specific value k, okay, which is just a placeholder, we're going to suppose that this is true. A sub k is greater than A sub k minus 1. And now we're going to apply the inductive assumption for the k plus 1 step. How do we do this? I'm going to start from the assumption, right? Start with A sub k is greater than A sub k minus 1, okay? So what does that mean? Well, I'm going to build my way up to showing the k plus 1 step, which is I'm going to first take 1 over A sub k, and I know that that's going to be less than 1 over A sub k minus 1. This is true, right? If we flip both of these, we're going to reverse the inequality. So negative 1 over A sub k is greater than negative 1 over A sub k minus 1. So 3 minus 1 over A sub k is greater than 3 minus 1 over A sub k minus 1. Notice, very cleverly, this is A sub k plus 1, and this is A sub k. So A sub k plus 1 is greater than A sub k. That's what we wanted to show. That's true. So therefore, so this is the conclusion, which is like I guess I neglected to say that's the last step of the mathematical induction argument, which is therefore, for all n greater than or equal to 1, A sub n plus 1 is greater than A sub n. Therefore, the sequence is increasing. So it's monotonic increasing, and we've just shown that inductively. So we've shown that this is true for the entirety of the sequence without knowing the explicit form of the sequence. Wild, huh? Okay. So step 2, remember that was all step 1. I know, it's kind of long. So that was all step 1. Step 2 is to show that this sequence is bounded. Okay, so our claim here is that for all n greater than or equal to 1, a sub n is less than, so remember, because it's increasing, we want it to be bounded above. What is it bounded above by? Well, jury is out exactly on what, we should aim for. But a good suggestion is maybe it's less than 3. Okay? So how do we know that this is a worthwhile place to start? Perhaps because the first term of the sequence is 1, and the next one is 2, right? So maybe it is less than 3 for the entire way, right? All right, so let's do our base case. N equals 1. All right, so a sub 1 equals 1 is less than 3. Done. It seems like, like why would we even bother with that, right? But we need to establish that it's at least true for 1. So the inductive assumption now is basically for the specific value n equals k, a sub k is less than 3. Okay? So the k plus 1th step is we want to show a sub k plus 1 is less than 3. Okay, so that's where we want to end up. We're going to have to start from the inductive assumption, though. We know a sub k is less than 3. So 1 over a sub k is greater than 1 over 3. So negative 1 over a sub k is less than negative 1 over 3. So 3 minus 1 over a sub k is less than 3 minus 1/3. So a sub k plus 1 is less than 3 minus 1 over 3 is definitely less than 3. Okay. In fact, that suggests that 3 isn't even the upper bound that we want, right? 3 minus 1/3 is the right bound. Okay, so what has this shown us? So our conclusion for all n greater than or equal to 1, a sub n is less than 3. In fact, it's stronger than that. We found a lower bound, an even lower bound, but we're not going to get into that. Then, okay, here's step 3. By the monotonic sequence theorem, we know because a sub n is monotonic and bounded, it's definitely bounded above, which is the one that we wanted, a sub n converges. To what, you may ask? Great question. And this is where we use a clever argument. So, but what is? Now, so the limit, right, which I'm going to denote as L, this technique won't always work. Sometimes it will be inconclusive, and that's okay. Just know that this is going to require some clever thinking, and the equations that we get are true in the limit sense. Okay, so there's going to be some weird algebra going on here. So if we write L as for the limit of this sequence, which we know exists, it's a real number, we know the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of a sub n plus 1. Okay. This statement here, it feels weird. It feels weird to say it, right? Like, what is this actually saying? What does this add, right? Remember, the limit really only says anything about the sequence in the tail of the sequence. So only once you get past a certain, a large enough value of n, are we actually close to the limit that we're talking about. And it doesn't matter whether you start at the first value or the second value. The first however many values don't actually affect anything. It's what happens as you get further and further out. So this is where the notion of infinity is kind of messing with our intuition, right? All this is to say, we're saying if we think about what a sub n plus 1 actually is, right, and apply the limit laws, then we have 3 minus 1 over the limit as n goes to infinity of a sub n. We know that this equation has to be true because by the limit laws, as long as that limit exists, then we're allowed to do this. Okay, so this is the weird part of the process. But this is just, we're going to call that L. We're going to stop worrying about all the limit notation. We're going to call it L equals 3 minus 1 over L. Okay, so L squared equals 3L minus 1. Okay, so L squared minus 3L plus 1 equals 0. Whew. Okay, so at this point we have a quadratic equation, and we can use whatever machinery we want to find out what L has to be, including the quadratic formula. So 3 plus or minus the square root of 9 minus 4 all over 2. Okay, this gives us technically two values, which should be impossible, right? Limits are unique. There's only one limit here. But L is not greater than 3, right? How could it be if we can't go past the lower bound? We'll make sense of this in a second. So it has to be that L is equal to 3 minus the square root of 5 over 2. And that's it. That's your limit. So bizarre, right? How does that work? It doesn't always. But when you can find the limit this way, it's really clever. Okay, so now we're going to go back to the beginning, which is to say, this is the part where you can safely skip this if you're not terribly interested in finding out how the cheese is made. But just know that this is the underlying math of the theorem. Okay, it's at this point where we're going to need a few preliminary definitions, more precisely than we did with before. Okay, so we have some already, right? So for instance, what it means for a sequence to be increasing, what it means for a sequence to be bounded, right? So let's go over bounded real quick, okay? Definitions. One. Okay. So we're going to call M is an upper bound for the set S if for all x in S, right? I could use that weird notation, but I'm going to avoid it as much as I can. M is greater than x, okay, or equal to. 2, and there's your corresponding definitions here for lower bound and what I'm going to show you now, but I'm going to stick just to the first case, right? Case 1 of the monotonic sequence theorem. So let me go back real quick. The monotonic sequence theorem, of course, we've been focusing mostly on this case, okay? And I'm going to stick to that, okay? So we say lambda is a least upper bound for the set S if two things apply, right? So the first property that this needs to hold is that for, first of all, lambda is an upper bound for S. It makes sense, right? We're just qualifying what kind of upper bound it is. 2, if M is any upper bound for S, lambda is strictly less than M, or less than or equal to, I'm sorry. Yes, okay. So what does this mean? It means this is the part that's qualifying what it means for it to be a least upper bound, okay? So the first condition is saying lambda is an upper bound, right? So it's larger than all the values in S. And if we encounter any other upper bound, that upper bound has to be greater than lambda. In other words, lambda is the smallest among the set of the upper bounds for S, okay? Okay, so there's a lot of layers to this already, okay? But one really important part here is that lambda is unique for a set S, okay? So it is a real number. All we're talking about here is sets of real numbers, right? So think intervals, or intervals with gaps even, or just, collections of real numbers. Okay, the last thing that we need before we can fully state this is what is really technically called the completeness axiom. And it's something that we take for granted. That's what axiom means. So the completeness axiom states that every set of real numbers, S, that is bounded above, so in other words, that it has an upper bound, has a least upper bound, lambda. So any set S that's bounded above gets a least upper bound by default. That's the completeness axiom. Does it sound like that is what we're saying, that the real numbers have no gap? It doesn't sound like it. It's really weird that this gives us that, but it's true. Okay, so now we're going to say, okay, now we're going to sketch the proof, okay? So the proof sketch. We want to show that the sequence A sub n, assuming it's bounded and monotonic, increasing and bounded above, has a limit. Okay? So, in other words, the meat of this proof is going to be using that limit definition, right? For every epsilon, there exists an n, etc. Okay? So, we're going to need that to be the outline, okay? Our candidate for the sequence is let lambda be the least upper bound for the set S being the range of this sequence. So the range of the sequence is just all the terms, right? So think of all the terms in terms of a set of real numbers, right? So for instance, in that first example we had 0, 1/2, 2/3, 3/4, that set. Think of that set, okay? So because it's bounded above that set, then it has a least upper bound, and that's what we're going to call lambda, okay? We are going to show that lambda is in fact the limit of that sequence. Does that make sense? Why that would have to be? Maybe not. But the important thing to recognize here is that we're going to need to recreate that argument for showing that the limit exists. So in other words, for fixed epsilon greater than 0, we'll find an n, so that's an n, sorry, for which little n being greater than n guarantees that a sub n minus L, an absolute value vars, is less than epsilon. Okay, how these things connect is going to be super bizarre, and it's basically going to be the key is that the fact that L minus epsilon, or sorry, I'm going to use lambda. Let me use lambda. So the key is that lambda minus epsilon, so the least upper bound minus that epsilon, tiny amount, cannot be an upper bound for S, the range of the, okay, so in other words, if we think about this sequence, right, the sequence is increasing, getting closer and closer and closer, right, to this limit, which I claim is the least upper bound, okay? And I'm going to take some tiny, let me call this lambda minus epsilon, right? Just below it. My claim is that there is some point at which the sequence will cross that dashed line, and it will never come back down. It's clever. It really is clever because it's monotonic, right? So because it's monotonic, it's always going to go up, and it's going to cross that line at some point, and then it's going to be trapped in that epsilon bound. Okay, so if you're following along, I know it's a lot. So one really good thing that I want to point out here that, you know, may help if you're feeling like, oh my God, where is this coming from? It's okay. You're not expected to follow along perfectly. You're not expected to be able to reproduce this argument. You're not expected to even know where any of this came from. I'm showing you this because this is the math that underlies the monotonic sequence theorem. And the sooner you see it, if you're going to be a math major, the better. Because you'll start to see some of these really deep, interesting arguments. And if all you take away from this is this picture, great, okay? But it would be wrong for me to not present this, right? So, with that said, the proof sketch is really for us to organize our ideas. The actual proof is actually very succinct and nice. So, proof. Let a sub n be a monotonically increasing. That doesn't say monotonically. Pretend that says monotonically. A monotonically increasing and bounded above sequence. That, I think, grammatically is wrong. I think it should say sequence that is bounded above, but you know what I mean. So the range, which is a set, S equals the set of all terms of the sequence, is bounded above. By the completeness axiom, which we're just taking for granted, remember, S has a least upper bound. Lambda, okay? That has the least upper bound properties, okay? We're gonna come back to that, okay? Fix some epsilon greater than 0. That's going to be our tolerance, okay? Now, lambda minus epsilon cannot be an upper bound for S, okay? This is because lambda is the least upper bound. So anything less than that cannot be an upper bound for this set. Okay. So because this is true, then there is some n natural number such that a sub n, capital N, is greater than lambda minus epsilon. Okay. Since the sequence is increasing for all n greater than or equal to capital N, a sub n is greater than lambda minus epsilon. Little n now, okay? So this right here is that first term that crosses the boundary. And every term after that is in that zone. Now, we can rewrite this as, because this is an inequality that we can manipulate, as if we subtract epsilon from both sides and then subtract a sub n from both sides, then we get lambda minus a sub n is less than epsilon, and has to be greater than 0 as well. All of this is to say, therefore, lambda is the limit of the sequence by the definition of the limit of a sequence. And so a sub n converges because it has a limit. That's it. Proof. QED. All right. So this is the justification, full justification, by the way, right? We didn't skip any steps here, of the monotonic sequence theorem. Whether you can follow this argument or not, right? It takes practice. It takes time to digest these ideas and definitions, and yes, it also needs you to develop some intuition. So don't stress out about it. Okay? The important part here is the picture, which is to say, at some point, a monotonic and bounded above sequence is going to cross a threshold, after which point it's going to be within epsilon of the least upper bound of the range of that sequence, which is the limit of the sequence. Okay, so that's it for this section. In the next video, we're going to talk about series.